Last time we defined what a hyperplane in Rn is. We decided to refer to an n-1 dimensional affine subspace of Rn as a hyperplane in Rn. But now that's in terms of some point, a singleton set from Rn plus an n-1 dimensional subspace. That's an n-1 dimensional affine subspace. But we wish to find an equivalence with what we are accustomed to from analytic geometry in defining points, lines, and planes. But in order to do that, we need some, I need to remind you of actually one basic theorem from linear algebra. Now let's start with that. Now let V1, V2 be finite dimensional real vector spaces. Well, in fact, we only need V1 to be finite dimensional, but never mind. Since we will be dealing with Rn and its subspaces, everything is finite dimensional. Now let T on V1 to V2 be a linear function. Write R sub t for the range of this, that is f of V1. Well, if it's onto, then that will be V2, but in fact, a map which sends every vector in V1 to the zero vector in V2, that's a linear map as well. And n sub t, the set of all vectors in V1 which are mapped onto the zero vector of V2. What can we tell about R sub t and n sub t? Will they be subspaces of V1 and V2 respectively? Now, they will both be subspaces. R sub t will be a subspace of V2, n sub t will be a subspace of V1. How do we call them? R sub t is the range space of the linear map T, and this is the null space of the linear map T. Now, n sub t is a subspace of V1 called the null space of T, the map, and R sub T, that's a subspace of V2 called the range space of T. Now, the main result in this theorem is the dimension of n sub t plus the dimension of R sub t, they add up to the dimension of V1. We will not go through we will borrow this from linear algebra, but this proof is easy to access, and also intuitively it's clear. This is V1, this is V2. Now, the larger the null space is, the smaller the range space will be. Because you will have actually equivalence classes given any point in here. If you consider its pre-image as a set in here, they will be all of the same size, in a sense. So the larger this is, the number of points or the size of R sub t, the number of points or the set of points in V2, which have pre-images, that will become smaller. And that is arranged in such a way that this sum stays invariant and is equal to the dimension of V1. In the proof of the main theorem here, well, we will also use some basic facts from linear algebra, but let me mention them when their turn comes. Now let M be a subspace of Rn. M is a hyperplane in Rn if and only if there exists a non-zero vector in Rn, which is now the generalization of a normal vector to a plane in R3, a normal vector to a line in R2, and some real number R such that M is just the set of all x in Rn such that h dot x is equal to R. Now we also noted the importance of this representation. Well, what we expect is that a hyperplane in Rn will divide Rn into half spaces, into two half spaces, and well, one half space will be the set of all x in Rn such that h dot x is larger than or equal to R, and the other those x in Rn for which h dot x is less than or equal to R. Well, it's difficult to imagine what that means in terms of an n-dimensional subspace and so on. So for separation results, starting next semester, we need this representation. Proof. Let us first start by assuming that M is a hyperplane. Well, then it's in particular an affine subspace of Rn. Then M is equal to some M plus a subspace W. But now, the dimension of an affine subspace that was defined as the dimension of the associated subspace, so n minus 1, that must be the dimension of W for this to be an n minus 1 dimensional affine subspace of Rn, that is a hyperplane. And an n minus 1 dimensional subspace of Rn. W, subspace W of Rn. Now, what's the definition of the subspace being n minus 1 dimensional? It has a basis consisting of n minus 1 vectors. And any basis, we know, will consist of precisely n minus 1 vectors. But again, it's a basic fact in linear algebra. We can take these n minus 1 vectors, which form a basis, as an orthonormal basis. Well, normal, their norms will be equal to 1. In fact, once you have any basis, you can make the sizes, the lengths, the norms of the vectors in the basis 1, just by taking the same, by scalar product of that. And normal means any two of them, any two distinct of them, should be orthogonal to each other, which in terms of linear algebra means that the inner product should be equal to 0. So let us take an orthonormal basis for W. Now let y1, yn minus 1 be an orthonormal basis for W. Now let me write this in detail. That is, for all ij in 1 to n minus 1, the norm of yi of each of them, that should be 1. And if I is different than j, that should imply that yi, yj, the dot product, that should be 0. The standard basis vectors for Rn, they form actually an orthonormal basis. The norm of each is 1, and any two distinct of them, they have an inner product which is equal to 0. Okay, now let us try. Well, we need to find some non-zero vector h and some real number r. But now, this m here, it's a member of cap M. So if we find a candidate for a normal vector, for a non-zero vector, which will do the job as h, then r will automatically be determined. M should be in cap M. If h is given, for m to be in this set, h dot m, that will be equal to r. Okay? Now, what's a natural candidate for h here? Now, this is an n minus 1 dimensional subspace. Now, well, the intuitive idea is that H should be a normal vector to the hyperplane in here. So, well, if we can find some vector from outside W, which is orthogonal to each of these y1, yn minus 1s, because anything in W, this is a basis means, take any point in W, that will be equal to a linear combination of these. If I find something which is orthogonal to each of the y sub i's, then y dot that will be equal to 0. So it will be orthogonal to any linear combination. But again, we know from linear algebra, we can extend this to an orthonormal basis of Rn. That is, there is some yn, well, that must come from outside W, which has norm 1, which is orthogonal to each of these, that is, its dot product with any of these, its inner product with any of these is 0. And when we join that to these n minus 1 vectors, we will obtain a basis for Rn. Now, there is some yn in here such that yn has norm 1 for all I from 1 to n minus 1, yn dot yi is 0, and y1 to yn minus 1, yn is a basis for Rn. So this will also be an orthonormal basis for Rn. Now set H equal to y sub n and R equal to y sub n dot n, because this is the only point we know from cap n. Okay? Well, let's check whether this specification of H and R will do the job. We have to show that cap n as a set is equal to this set. That is, this set, singleton m plus w, should be equal to this set. Well, let's check. So let us start by taking any point in cap n. Let x be in cap n, which is m plus w. Now, x is equal to m plus some w for some w in w. But now, y1 up to yn minus 1, that's the basis for w. Thus, we can write this lowercase w as a linear combination of y1 up to yn minus 1. Now, w is equal to alpha 1 y1 plus alpha n minus 1 yn minus 1 for some real numbers alpha 1 up to alpha n minus 1. Now for this x, arbitrary point from cap n, to belong to this set, well, it should satisfy this. It's in Rn, clearly, the vector. So let's compute h dot x and see whether it's equal to R. Now, h dot x is equal to, so this is equal to this, h dot m plus h dot w, but that is h dot m, that's R, plus h dot w is this alpha I, I from 1 to n minus 1. But now, using the inner product rules, this is R plus alpha I. Now h is yn. Let me write that, yn, I from 1 to n minus 1, so that each of these is equal to 0. Thus, this is equal to R. So whenever we take any point from cap n, it will belong to this set. Okay? For this choice of h and R. So m is contained in x in Rn such that h dot x is equal to R. But to prove equality, now we have to show that the opposite inclusion also holds. Well, then let us take any x from here, that is any x in Rn, satisfying this, and then show that it also belongs to cap n. Conversely, take any x in Rn with h dot x equal to R. Now we wish to show that x belongs to M, that is to this set. But for x to belong to this set, well, then x is m plus x minus m. X minus m should belong to w. Let's try to show that x minus m is in w. Well, how can we do that? Well, x minus m, that in particular will be in Rn. So y1 up to yn, including n, that's the basis for Rn. I can write x minus m as a linear combination of y1 up to yn. If it turns out that the coefficient of yn in that linear combination is 0, then x minus m will turn out to be a linear combination of y1 up to yn minus 1, but that simply will mean that it's in w because this is a basis for w. Now, as x minus n is in Rn, x minus m, that's equal to a linear combination of yi, I from 1 to n, for some beta 1 up to beta n in R. Well, what do we know? X is in Rn, but it has this property. So, well, somehow we have to use this. Now, h dot x minus m. On the one hand, this will be h dot x minus h dot m. What's h dot x? Well, that's r. What's h dot m? Well, that we took as the definition of r. That's r as well. So this is equal to r minus r, and thus 0 on the one hand. But x minus m is this, so this is equal to h dot beta I, I from 1 to n. But now again, using the rules that the inner product satisfies, this is equal to beta I, h was yn, let me write that, yn dot I from 1 to n. What can we tell about these? Well, when I is different than n, this will become 0. If I is equal to n, yn dot yn, that will be the norm of yn squared, but that will be 1. So this will be equal to beta n. But now beta n is 0. So x minus m is equal to the sum of beta I from 1 to n minus 1. But that simply means this is in W. So x equal to m plus x minus m. That will belong to m plus w, which is just m. Hence, we also have shown that the set of all n vectors, x in Rn, with the property that h dot x is equal to r, that's in m, so m is equal to x in Rn, h dot x is equal to r. So this is just the only if part of this. We have shown if M is a hyperplane, then it has such a representation. Now if we start with any non-zero vector h and any real number r and form this set, we need to show that it is a hyperplane. That is, it is an n minus one dimensional affine subspace of Rn, to also prove the if part of this theorem. Okay? Well then, conversely, assume that there are a non-zero vector in Rn and a real number r such that r set cap m is equal to x in Rn such that h dot x is equal to r. We will now show that this set is a hyperplane. Well, that we have to find some n-1 dimensional subspace of Rn such that this set is equal to some singleton, any point from here, plus that n-1 dimensional subset. Now first check whether this is non-empty, because we also need to take one point from here, not just the subspace. Now set y equal to r times h over the norm of h squared. This will be in Rn because this will be different than 0 since h is a non-zero vector. Now, h dot y, that will be r times h dot h divided by the norm of h squared, that's r. So y is in cap m. It's not empty. Now, in order to find an appropriate n-1 dimensional subspace, well, here h dot x is equal to r, but let's consider the map on Rn to R, which sends each x in Rn to h dot x. When the value of that map is equal to R, the set of all such points, they will comprise cap M. Let T on Rn to R be defined by T of x equal to h dot x for each x in Rn. So this will be a real value. Will this be a linear map? Now clearly so, but let's just check for any alpha beta in R, xy in Rn. Let us consider T of alpha x plus beta y. This should be equal to alpha tx plus beta ty for T to be linear. But what's the definition? This is equal to h dot alpha x plus beta y. But now we have the inner product properties. This will be alpha times h dot x plus beta times h dot y. But this is simply alpha tx plus beta ty. So it is only the inner product, not the fact that it's the usual inner product, but that it's an inner product. That makes this function a linear map. So T is linear. Now, as I have started the lecture with this theorem, which we haven't used yet, well, that must be of some use in completing the proof. So, well, if that's the case, what from here would you take as a natural candidate for W, which will be the subspace associated with cap M? Now, probably this, Because H dot M, that will be R, if M is in cap M, well, then we need the linear map in here be such that, well, those points which are sent to 0. Okay, now, well, let me write that as a claim. Now pick M from M. We can do that because we have shown that it's non-empty. Okay? M is non-empty. Well, I could this way as well, but take any M in M. We claim that M is the singleton M plus the null space of this linear map, NT. Well, for any x in M, x is equal to M plus x minus M, where T of x minus M, which is h dot x minus M, which is h dot x minus h dot M. What do we know about x? It's in M. What's M? M is this function at this set. So h dot x, that's equal to R, and h dot M, that's equal to R as well. So this is equal to 0, which means, so x minus M is in the null space of T, so x is in singleton M plus NT. Thus, M is contained in M plus NT. Now let's show the converse as well. Now let us take any point from here. Well, that amounts to taking any point from n sub t. Take any x in the null space of t. Now, h dot m plus that, this will be equal to h dot m plus h dot x. But this is R, since m is in cap m. This is 0, since x is in the null space. So this is equal to R. But then that means that m plus x is in cap m. Thus, m plus the null space, that is in cap m. So we have proven this. So this n is an affine subspace of Rn, because it's of the form some singleton m plus some subspace. What remains to be shown is that n sub t has dimension n minus 1. Well, we will use this now. Well, do we know what's V1 in this context? our linear map is on Rn to R. So V1 is Rn, it has dimension n. What's the range space? Well, we know that the range space is a subspace of R. What are the entirety of the subspaces of R? It's R itself and singleton 0. Because if it contains some non-zero member, a subspace, well then by just multiplying that by scalar, which has to be in that subspace, you can get the entire R. So, is it possible that the range space of this is singleton 0? No. Now, what, for example, T of H? H is in Rn. This is H dot H, but that's different than 0. By an inner product property again. Even if it were not the usual inner product, this would hold. So, R sub t is not this. So, R sub t is equal to R. Now, by this theorem, n, that's the dimension of Rn. This is equal to dimension of Rt, but that's R, plus dimension of Nt. But this is n, this is 1, so dimension of Nt is n minus 1. Hence, let me just write here. M is an n minus 1 dimensional affine subspace of Rn, that is a hyperplane. A hyperplane in Rn. Completing the proof of this. Any questions about this? Okay. So that actually completes what we aim to cover this semester. Next semester we'll start with separation theorems. Well, and the separating object will be a hyperplane. So we have that ready. In the time which remains, we will discuss now the exam questions. Well, if we cannot finish with that today, we'll continue for some time on Tuesday as well. But on Tuesday, well, when we consider the introduction of the course, the first hour, that we would be coming back to that at the end again. Because all introductions turn out to be more meaningful when you close the course. Well, then you have the yardstick of whether you have achieved what you have declared at the beginning. Okay? And by the way, if you have concerning homeworks, exercise sets, or anything else, if you wish me to send you written solutions, please let me know. But I should have some time before the final exam, so if it's a last-minute thing, then I may not be able to do so. So did you solve the question you asked? One more. Now, well, let me give one more hint. And that question, that was a homework question, homework 9, that has a record in having a short solution. It is the shortest solution among all homeworks in 515 over the last 25 years. But the hint is, I said, don't try to use the definition of, it's not a question in differentiation. Its result tells us about what happens to the derivative if you move away in the direction of, from the point in the direction of the gradient of the function. So it gives information about the derivative. Cauchy-Schwarz, you had this Jacobian, then you had a vector in RP. Well, that matrix product is nothing but the inner product of two. And we have the Cauchy-Schwarz inequality. If you don't do it in the break, I'll start by doing that because it will take no time, okay? Now let's have a break first.